In this section, we talk about a very important theorem called the Cauchy-Goursat theorem. We first do some review for the undergraduate level theorem. We have the green theorem before. I think you learned this theorem in the sophomore year in the course of engineering mathematics or applied mathematics, such and such. I like to rewrite the theorem here. Let me do some modification. Okay, now it looks better. Huh? Here we have P and Q, P dx plus Q dy. P is a function and Q is a function too. We integrate this differential form along a closed curve called C. This is the contour integral. You can look at the website, see what contour integral is, or you can look at the book of engineering mathematics. We integrate this differential form P dx plus Q dy along a closed curve C. Like this, we have a xy plane, and along in this plane we have a closed curve C. C is a closed curve, and the domain or the region bounded by this closed curve is named as R. This is R. Okay. According to the green theorem, we do not prove this theorem here, okay, because it is an undergraduate level theorem, so we don't give you the detail here. You should pick up by yourself. The green theorem tells us that P dx plus Q dy integrated over the closed curve will be equal to the what? The two-dimensional area integration. Okay, P dx plus Q dy integrate along a curve, but now we can change it to the integration on a two-dimensional plane, which is just R. Okay, we change the integration along the curve to the integration inside the curve. Okay, this is the integration for the area bit by bit. Okay, this is a small element, area element. Okay, and then Q dx plus P dx plus Q dy integration along C will be equal to partial Q partial x minus partial P partial y. Okay, integrated inside the region R here. This is the result of green theorem. Okay, what will be the direct implication of this theorem? This theorem tells us that if partial Q partial x equal to partial P partial y, then this one will be equal 0, right? So according to the green theorem, if partial Q partial x, now we are talking about the upper right hand, the upper right part of the backboard. Huh? If partial Q partial x minus partial P partial y equals 0, then the integration of P dx plus Q dy equals 0. this is a very important result. We will use it to prove the Cauchy-Goursat theorem later. If partial q partial x minus partial q p partial y equals 0, we have this one equals 0. So this area integral becomes 0. So as a result, the contour integral is 0 too. So if these relations hold, then this contour integral is equal 0. Okay. What will be the important implication here? Let us consider an analytic function fz. Fz can be written as u plus iv. U and v are real value functions. This is the real part, and this v is the imaginary part of the real of the complex value function. F equal to u plus iv. Okay, and also dz equal to dx plus I dy. And then we multiply this function to the differential dz here to get the result lower. Okay, f dz equal to f plus iv times dx plus iy equal to what? U dx and then minus v dy, because I square equal to minus 1. And then v dx and u dy times I here. So we can regrouping the terms such that to know that f dz equal to u dx minus v dy plus I v dx plus u dy. Okay, let us repeat this result here. We integrate a function fz along a cos curve C. Okay, the cos curve C is drawn in the right hand side of the breadboard. Okay, we integrate along a cos curve C here. Okay, and then u and then f can be written as u plus iv. dz can be written as dx plus iy, and then the result will be f dz equal to u dx minus v dy and time I v dx plus u dy. This result have been obtained before in the just last moment. We just obtained this result. Okay, and then now I want to tell you this integral will be equal 0, and this integral will be equal 0 too if the function f is an analytical function. Okay, let me carry out this calculation carefully. In order to make clear, I want to give it a name. This integral as a and this integral as b. Okay, let us consider integral a first. Okay, here. Okay, in the second line of the breadboard, a. A is just integral of u dx minus v dy, right? Okay, here we put this integral downward, and then we apply the Green theorem. According to the Green theorem, we just try to perform the partial differentiation with respect to minus v and the partial differentiation with respect to u. Why? Because u dx minus v dy equal to p dx plus q dy. Okay, in a standard form. So now q is minus v, so we put q here according to the Green theorem, and p equal to u, so we put p here according to the Green theorem. Now we turn this this contour integral into the area integral like this, and then this will be equal 0 if the Cauchy Cauchy-Riemann equation for analytic function holds. What do you mean? If the function fz is analytic, then according to the Cauchy-Riemann equation we talked about before, f equal to u plus iv, and then Cauchy-Riemann equation tells that partial u partial x equal to partial v partial y, and also partial u partial y equal to minus partial v partial x. You can check these relations carefully in the previous lecture notes by yourself. Please check it now. And then according to the second part of the Cauchy-Riemann equation, we'll put it here. And then according to this one, we'll put it here. According to this one, the integrand here equals 0. Okay, we put this equality here to show that this integrand is equal 0, right? Understand? So this integral equals 0 if the function fz is analytic. If it is not analytic, we cannot draw this conclusion. But if fz is analytic, then we have this conclusion. In the same way, we can show the second part, the b part of the integral in the first line, right here in the third line. In the same way, we apply the Green theorem to get this, and then apply the Cauchy-Riemann equation to get the 0 here. So as a result, the integration of an analytical function or analytic function or analytical or analytic function, both ways can be applied. Or somebody call it analytical function, an analytic function, but it doesn't matter. Okay, if fz is an analytic function, the contour integral along C will be equal 0. What do you mean? It is a very, very important result, because see here, the contour is arbitrary. We didn't mention the precise location, the size, the shape of the contour. It can be a crazy shape, okay, as crazy as you want. A very, very crazy shape, like we will show it before later. We can have a crazy shape here and crazy size, very, very small contour or very, very big. It doesn't matter. So this contour is arbitrary, and fz is also arbitrary. The only requirement is fz is analytic. It can be anything, any function we had shown before. Remember in section 1.4, section 1.4, I had already shown you a lot of examples of analytic functions, like the cosine function, sine function, exponential function, power function, fractional function, and polynomial functions, and hyperbolic sine, cosine function. All these functions are analytic functions. Now, all these analytic functions, when it is integrated along a closed curve, any closed curve, you will get 0. Okay, it is a very important result. Okay, you may ask a question, Professor. When you integrate an analytical function, you get 0. You get nothing. How come it is important? It is an interesting question. You get a 0, and 0 is important to many people. 0 is nothing. But but here you will have the experience that you get the equality. You get the integrand equals 0, integral equals 0 as an equality. It is a very important result. You will see later. Okay, be patient. Okay, we talk about the Cauchy-Goursat theorem here. This is the title of this section. It is a very important theorem. What is the Cauchy-Gaussian theorem? I show you. I just get the lengthy statement of this theorem. I just want to give you the precise mathematical expression of it. Okay, Cauchy-Gaussian theorem tell you that if you integrate any analytic function along any closed curve like this, any closed curve C in the right hand side, any closed curve C, you integrate any analytical function along any closed curve C, you get nothing. You get 0. This is the Cauchy-Gaussian theorem. Okay, and it is very important. I tell you, you will see it later. Before you see the importance of this theorem, let me show you a simple example. In this example, I select fz as sin z. Of course, we mentioned this function before. It is analytic on the entire plane. It means that at any point, every point on the plane, the function is analytic. It can be differentiated. Okay. Now, we choose a closed curve like this, gamma. Okay, closed curve gamma. The angle of the gamma is A, B, C, D. Okay, A, B, C, D. Since I had already used capital C here, I cannot use it for the curve, so I use gamma here instead. So see, the closed curve gamma here is, in a very strange shape. It is weird shape. It doesn't matter. It looks a little bit like a diamond. Whatever. I just choose it arbitrarily. I just want to show you that the Cauchy-Gaussian theorem can be applied to very strange closed curve. Any shape, any size, any place. Okay, we choose this closed curve and apply the integral to the function fz here, fz equals psi, and then do we need to calculate this integral along the curve bit by bit? I tell you, we don't need to, because according to the Cauchy-Gaussian theorem, because sin z is analytic, so according to the Cauchy-Gaussian theorem, it must be equal to 0, the integral. Okay, so we don't need to integrate from A to B and B to C, C to D, and then D to A. You don't need to do this, because we have already proven this result. So long as this curve is closed, so long as this function is analytic, we will have the result of the integration equal 0.